certificate in non-convex case is like gradient of fx star minus now your polynomials. Sigma gj of x is equal to 0. And also for the KKT conditions, when f and minus j are convex, you can write f of x minus f of star minus lambda j star f of x minus f of star minus I from 1 to m sigma j star of x, this is SOS, gi of x. And sigma j star of x star is lambda I star. So let's talk about slightly different things, but you will see how SOS plays an important role in several problems in graph theory. Graph eigenvalues, let me remind you, your adjacency matrix, you can write it as A, D minus D. Also for the regular graphs, you know that you can write it as this. And also your Laplacian, which is positive definite, you can write it as I minus A of G. And you know the first eigenvalue of your Laplacian is 0, and the second eigenvalue of your Laplacian, you relax it for the real values, so Lg of x, x transpose x. So this is equal to minimum of, by definition, of course, omega ij xi minus xj squared. This is sum of squared. So this is an example of SOS, but this is a very simple example. You cannot use locality. Di xi2 is greater than 0. So Perron and Frobenius, they said that if lambda 2 is 0, if graph is disconnected. So you have partitioned your vertices like this, and your graph is totally disconnected. And if lambda 2 is near 0, very near to 0, then graph is very close to disconnected. Another important related thing is Shiger inequality. I just review it, maybe I've told you before, but Shiger inequality says that lambda 2 over 2 phi of g is, your edge expansion is sandwiched between upper and lower values. But the second eigenvalue plays an important role. So a simple proof, the proof sketch is like this. You say that lambda 2 is minimum of sum of over all ij's omega ij xi minus xj squared over di xi squared, which is minimum of omega ij xi minus xj squared. Here x was in Rn and x is orthogonal to D. So because it is orthogonal, so you don't mind if I write this as xi minus 2 minus 0. So instead of 0, I write di xi squared over sum of the i's. So this is already 0. So what I do is that because it is in Rn, so it is relaxed and it has the potentiality to go less than our original problems, which is omega ij xi minus xj squared, and this one is now discrete. And so dixi squared minus dixi squared, same as before here. We just use this fact that it is a relaxation of that. And then this is equal to minimum of W of S and S bar, W of your vertices, W of S, W of S bar, and this is less than 2 phi of G. I just recall that phi of S is omega of S and S bar, minimum of, this is your expansion, edge expansion, not vertex expansion. These are two different things. But edge expansion is, everybody knows about edge expansion. Few people know about vertex expansion because it has its own Cheeger inequality, it has its own Cheeger algorithm, and so this is minimum of omega S and omega of S bar. And the Cheeger algorithm that I said, Cheeger algorithm, is just that your spectral clustering that you know. It means that you get your eigenvector of your Laplacian eigenvector of your Laplacian G for the second eigenvalue, because the first one is 0, and then you sort your x such that x1, so your eigenvector x is like this: 1, 3, 2, 5, 7, and then you sort it x1, x2, xn. For example, here 1, 2, 3, 5, 7, and so x1, x2, x3, xi plus 1, xn. And suddenly you say, okay, from here I want to say that this is the cluster Si and this is the cluster Si complement. And you consider subsets of Si, and finally you take your S to be arg mean of phi I of SR. And so this is a Cheeger algorithm that you know from spectral clustering. So the big question is that the Cheeger inequality for vertex expansion. Of course, I should recall what is vertex expansion. It's different from edge expansion. This is also fundamental in graph theory. Vertex expansion, it asks how many vertices are near your S. It means that if V of S is equal to the neighbors, inside neighbors of S plus neighbors out S over minimum of S and S bar. This is as usual. So what we say, that phi of the graph G is minimum of over all such expansions. So expansion of a graph is just the minimum over all expansions that is possible. So here you have some S. So you have some S, you have some internal neighbors of S, and then some in outs of S is there. And then you want to see how many, for example, why this is important, because if this is the case, if each of these vertices goes to 2, 2, 2, 2, you will see that it is using the vertices. It's like a maximum entropy. You are using the maximum possible potentiality of talents. But if you waste that, for example, you will see that one of these nodes goes to several nodes, but the rest of them are just going to one nodes. Then you have failed using the potentiality of the talents. I say talents of these nodes. But this is good, this is bad. So it has a basic intrinsic meaning. So there is a meaning behind that. Because, for example, you are wasting your resources here, but you are using all of the resources in your routing, in any problem that you have. So it's like finding neighbors and which of them are wasted or not. And so the expansion of your vertex expansion, you can write it as minimum of maximum xi minus xj squared. So it means that over I, to maximize over all j's such that ij is an element of edge, is an edge, over xi2 minus 1 over n xi squared. So this is minimum of neighbors of S union neighbors of S complement, S complement over N. So we relax it. So let's call it L infinity to be minimum over X in Rn, but X is orthogonal to 1. In order to separate S and S bar, we should say that, for example, which one of them are 1, which of those are minus 1. So this one, it means that xi is equal to 0. So minimum of, as I said, I maximum j such that ij is an element. Xi minus xj squared. So for each vertex, it means that for each vertex in S, we only count one event. Even if it goes to many vertices in a spar, we are just counting one. So we can handle the potentiality if his talent is wasted or not. And the theorem of Bobkov and Hoodrer and Tertali in 2000, it says that lambda infinity over 2. So same with the same split of that edge expansion. Now here for vertex expansion, it is sandwiched, but this time we have C lambda infinity. And you know that lambda infinity is minimum of that. So it's here. So what I want to say is that how do you compute this lambda infinity? How do you compute it? And you answer, use SDP as you use for many problems in computer science. So in SDP we minimize, in the denominator everything is linear. I maximum j ij in E. So xi minus xj squared. So from numbers, you go to inner products. So you go to the Hilbert space. And so it's so beautiful. For example, when I say something xij, so it's a scalar, but you can see it as an inner product. So you go to Hilbert space. So it's very interesting that how Hilbert space can be touched, can be understood, and why it is so natural. Because in Hilbert space, 2 points, it's like inner product spaces and Hilbert spaces is very essential for hypergraphs. And it is so strange for me that nobody even says this, that Hilbert spaces and inner products are essential for understanding hypergraphs and extending all of the graph problems and graph approximations from graphs to hypergraphs. In order to understand that, what do you mean by nonlinear spectral clustering, those things. But Hilbert space is so tangible. So a theorem from Steuer and Tetali says that lambda infinity phi of g is less than C SDP that we have calculated, and this is less than C L infinity log D. And it has, so vertex expansion, just like edge expansion, has its own Shiger algorithm. So you might say that it is spectral clustering for vertices. So the Shiger algorithm for vertex expansion is like this. SDP, you find vectors x1, x2, xrn, and we just want to use the same trick that we used for max cut. I explained it in my playlist for max cut, how do you round it. You want to do it for this vertex expansion, small set expansion. So the rounding mechanism that we used, so it's a randomized rounding again. So if we pick a random Gaussian vector G, and we project and sort according to xi dot g, and then apply a Shiger sweep to sort a vector, or we can say pick a random threshold cut. So it's very easy. It's just like the idea of Guemans-Williamson's in max cut. You are doing it for vertex expansion. So that's the importance of paradigms, because if you learn how to solve a problem, you can solve it, you can use that paradigms for many, many problems. And that's why many people write hundreds of papers. And so SDP formulation for max cut, we talked about max cut, why not talk about SDP formulation for max cut? I talked about max cut in part 5 of this playlist, and so the problem is that we want to maximize ij in E, but now zi is in -1 and 1 is discrete. 1 minus zj over 2, so this is the optimal of G. So the interesting thing is that this can be embedded into Sn-1, which is all vectors that are length 1. I mean, how do you do that? So, for example, for -1, it goes to 0, 0, 0, 0, -1. For 1, it goes to 0, 0, 0, 0, 0, 0, 0, 1. And for x, so it goes to 0, 0, 0, 0 to x. So this is how you embed it into Sn-1. So this problem 1 can be written as problem 2. So you write it at maximum of 1 minus ui transpose uj. So I'm just reviewing max cut. And how do you use SDP for that? So every solution of 1 has a corresponding solution for 2. And also 2 is a relaxation of 1. And then we conclude that 2 has more solutions because it is relaxed. And because it has more solutions, so we expect, because it's a maximization, we expect that this relaxed one is very relaxed and it has higher values than your original problem. So this is bounded because, why? Because ui transpose uj is greater than -1. So it is bounded, and we don't have any problem with that. So SDP allows us to solve problem 2 efficiently. And so